This video is to give you a strategy for finding quadratic rules to number sequences. And I'm going to have two examples. This is example 1. So I've got a number sequence that goes 6, 14, 24, 36. The ends are just labeling the position in the sequence. So the first term, the second term, the third term, the fourth term. So for an exam question, if you're asked to describe any patterns that you see, it's not really a pattern to say that the n numbers go up by 1 every time. We're talking about the numbers that I've labelled as P here, P for pattern randomly. So I notice that to get from the 6 to the 14, I have to multiply by 2 1/3. Now that's easily obtained by doing 14 divided by 6 to see what you'd need to multiply the 6 by to get the 14. And then if I do the same thing with the 14 and the 24, I find that I have to multiply by 1 5/7. So 24 divided by 14 gives me 1 5/7. That's where I got that number from. So because that's not the same number every time, it's not a geometric sequence. So we can rule out the idea of it being a geometric sequence in terms of identifying what kind of a sequence it is. Well, now let's look at what I need to add from one term to get to the next. So from 6 to 14 is plus 8. From 14 to 24 is plus 10. And then from 24 to 36 is plus 12. So it's clearly not an arithmetic sequence because the number that you add each time isn't the same. Plus 14 for the next one would give me 50 because I'm seeing that a pattern is occurring there because the number that I'm having to add on is 2 more each time. So from that pattern, I can make a prediction about future terms in the sequence. Plus 16 for the next one, 66, plus 18, 84, plus 20, 104. So because I've spotted that the differences between the differences are 2 each time, then I can make a prediction for the rest of the sequence. Now these differences between the differences are called second differences. And that tells us that we've got a quadratic sequence here because it is a characteristic of quadratic sequences that the second differences are always constant. And in fact, if the second differences are 2, then that tells us that the quadratic term is indeed n squared, n being the position in the sequence. So what do I mean by that? Whatever our rule is, it's going to contain an n squared. So not a multiple of n squared, not a half n squared, not a 5n squared, but exactly 1n squared, or just n squared. So I'm going to try, if the rule was n squared, what numbers would I get? So when n was 1, I would get 1 squared, which is 1. When n is 2, I would get 2 squared, which is 4. When n is 3, I would get 3 squared, which is 9. And when n is 4, I would get 4 squared, which is 16. So comparing the numbers I'm getting from that to the numbers I actually want for the P sequence, to get from the 1 to the number I want, 6, I'd need to add 5 to it. To get from 4 to the number I want, 14, I'd need to add 10 to it. To get from 9 to the number I want, 24, I'd need to add 15 to it. And to get from 16 to the number I want, 36, I'd need to add 20 to it. So the values that we're missing, because they're going up by 5 every time, that's telling us that there must be a 5n in the rule, because every time the n goes up by 1, we need something that goes up by 5 every time. So we have to have a 5n in the rule. So we've already got an n squared in the rule, so we're going to try n squared plus 5n. then when we work that out, we get 1 squared plus 5 times 1 makes 6. 2 squared plus 5 times 2 makes 14. 3 squared plus 5 times 3 makes 24. And 4 squared plus 5 times 4 makes 36. So those are the numbers we want from n squared plus 5n. So the rule must be that p equals n squared plus 5n. And when you write a rule like that for an exam, remember to use the proper notation. So it's got a left and a right side. P equals something involving n, and we're using the proper notation for powers and for multiplication. We're not using weird arrows for powers, and we're not using little stars for multiplication, for example. Okay, here's example 2, a little bit more complicated. Let's see how we go. So I've got a number sequence that goes 5, 8, 17, 32. I've already checked that it's not geometric because 8 divided by 5 isn't the same as 17 divided by 8 or 32 divided by 17. It's not an arithmetic sequence because it's going up by 3, then 9, then 15. So it's not a constant difference that you're adding. So we are adding here 3 to get from the first term to the second, then 9, then 15. So if we look at the second differences, 6, 6, 6 every time. So just based on the second differences continuing to be the same, we could predict the rest of the terms in the sequence. So if the next difference is 21, then the next term must be 32 plus 21, 53. The next difference is going to be 6 more, so it's going to be 27. So 53 plus 27 gives me 80. Then if the next second difference is 6 again, the next first difference would be 27 plus 6, 33. And the next term would be 80 plus 33, 113. And then for the last one, well, if the second difference continues to be 6, then the first difference will be 39, and the next term will be 113 plus 39, 152. So we appear to have a quadratic sequence because the second differences are constantly 6. So remember I said if the second differences are 2, then the quadratic term is just a single n squared. On this occasion, the second differences are 6, 3 times as much. So that tells us that the quadratic term must be 3n squared. We must have a 3n squared in the rule. So I'm going to try a rule with 3n squared. So when n equals 1, 3 times 1 squared is 3 times 1, which is 3. So I'm getting a 3, but what I actually wanted to get was a 5. So I would need to add 2 to that to get the number I want. Next term, when n is 2, 3 times n squared is 3 times 2 squared, which is 3 times 4, which is 12. But I actually wanted to get an 8. So to get where I wanted, I'd need to take away 4 from that. Next one. When n is 3, 3 times 3 squared is 27. But I actually want to get a 17. So to get to where I want, I'd need to take away 10 from that. Next one. 3 times 4 squared is 3 times 16, which is 48. But I actually wanted to get 32. So to get to where I'd want, I'd need to take away 16 from that. So I notice that these numbers I'm needing to adjust it by are going down by 6 every time. So because they're going down by 6 every time, that tells us that the rule must contain a minus 6n, because for every 1 that the n's are going down, we're wanting to adjust it by minus 6. So I'm going to try it with a rule that says 3n squared minus 6n. So for the first one, 3 times 1 squared minus 6 times 1 is minus 3. Now minus 3 isn't the number we want because we want to actually get a 5. So to get from the minus 3 to the 5, we'd need to add 8. Next term, 3 times 2 squared minus 6 times 2 gives me 0. Now 0 isn't the term that I want to get an 8. So to get to the term that I want, I'd need to add 8 to that. Third one, 3 times 3 squared minus 6 times 3 is 9. Now the number I actually want is 17, so I'd need to add 8 to that. And then the next one, 3 times 4 squared minus 6 times 4 gives me 24. But to get to the number that I actually want, which is 32, I'd need to add 8 to it. So we need to add 8 to all of our values to get the values that we want. So we try it with a rule that says 3n squared minus 6n plus 8. And then when we do that, when n equals 1, we get 5, which is what we want. When n equals 2, we get 8, which is what we want. When n equals 3, we get 17, which is what we want. And when n equals 4, we get 32, which is what we want. So the rule is p equals 3n squared minus 6n plus 8.